This course is going to be a course on spectral theorem. In the first few lectures we will review the finite dimensional spectral theorem and the spectral theorem for compact self adjoint or normal operators. Then we will go on to Banach algebras and do spectral theorem for bounded normal operators on a Hilbert space. Okay. But the first few lectures are going to be something which you should know. This course is intended for people who know some function analysis, the first course in function analysis. So, we will quickly review these two topics, finite dimensional spectral theorem and the spectral theorem for compact normal operators. Okay. So, let us start. So, finite dimensional spectral theorem. So, this is something which you come across when you do a course in linear algebra. In other words, this is known as diagonalization of normal matrices, and that is what we will go through. One of the advantages of working with finite dimensional cases is that you know that the eigenvalues exist because you are on a complex finite dimensional vector space and things like that. So, eigenvalues exist, and for a normal operators what happens is eigenvectors with distinct eigenvalues are disjoint, and so one easily obtains a certain diagonalization, and that is precisely what we intend to do in this first two lectures. Okay. So, we consider Cn. So, Cn is the with the complex inner product. So, n dimensional complex space with complex inner product. So, how is it defined? I take 2 points in the in Cn, Z and W. So, that is simply j equal to 1 to n set j W j bar, okay, where Z is Z1, Z2 etcetera Zn, that is a point in Cn, and W is W1, W2 etcetera Wn, that is another point in Cn, right. This is the Hermitian inner product on Cn. Okay. So, we will always stick to Cn with this inner product. Okay. So, we are not going to write down an abstract complex vector space and say that it is equivalent to Cn etcetera. We will just do things on Cn. Okay. And on Cn we have the standard basis, E1. So, E1 is 1 comma 0 comma 0 n times, and E2. So, this is something which you already know, 1 0 0 and so on, and we have En to be the last basis vector, right, and we can write down a linear transformation from Cn to Cn, and we can get its matrix form using this basis, right. So, the way you write a linear transformation with respect to a basis which gives you a matrix form is you apply the linear transformation to basis vectors and put them as columns, right. So, remember that standard basis, this is also orthonormal basis, right. So, let us take a linear transformation from Cn to Cn, okay, linear transformation. So, well, T of z plus W would be equal to T z plus T W, and T of alpha z will be equal to alpha times T z, where alpha is a complex number, right. The scalar comes out, that is what you mean by a linear transformation. And the T you can, so you apply the matrix form, right. So, the matrix form matrix form of T is obtained by applying T to this standard orthonormal basis even e to E n and writing them as column, right. Matrix form of T is, well, you can write it like this: T E 1, T E 2, etc. T E n. Right. Remember that T E 1 is a vector in C n, so it is a column vector, right. So each T E j is a n vector, right. Think of them as column vectors. You will get an n by n matrix form for T, which we will write down. So let me go to the next page. Okay. So we can write the matrix form for T to be equal to some matrix Aij, where these Aij's are. So the Tej is the jth column. So Tej you expand in terms of the basis vectors Ei, and you will get Aij, right, I going from 1 to n. So the coefficients Ai are what comes there, and also notice that Aij is nothing but Tej. So you write it as a column and take the ith component, right. So that is how you write the matrix form for any linear transformation. Okay. So I will not distinguish between linear transfer. So once you fix a basis, the set of linear transformations and the set of matrices, they are same. Okay. So fix a basis, the linear transformations. So linear transformations from Cn to Cn, right. So linear transformations on Cn, this is identified with n by n complex matrices. Okay. So that's something which you have already seen in the linear algebra courses, and you know how the matrix changes if the basis changes and all that, right. It becomes a similar one and so on. So I will not get into any of those, and I will not distinguish between a linear transformation and a matrix. Okay. We have fixed this orthonormal basis, and that is how we identify a linear transformation with a matrix. Okay. So I will use the language linear transformation or a matrix. Okay. Both will mean the same thing. Okay. So a linear transformation, so this is a definition. A linear transformation T from Cn to Cn is said to be normal if T star T equal to T T star. What is T star? T star is the adjoint of T, right, where T star is the adjoint of T. Okay. So how is the adjoint defined? Well, if you take a matrix A, let us say Aij are the entries of the matrix, what you can do is you look at the transpose and complex conjugate of the entries, right. So A transpose bar, that is the A star, and that is the matrix you get if you formally define the adjoint of T using inner product. So let me just remind you this. So T x inner product with y is x inner product with T star y, right. So this will also make sense in the infinite dimensional case. Okay. All right. So let us go to the next page. Okay. So if T commutes with T star, then we say it is normal. So let me write down some definitions which you already know. So T star T equal to T T star, self adjoint means T equal to T star, and unitary T star T equal to T T star equal to identity. right. So, all these two class of matrices or linear transformations are of course contained in normal ones, right. So, these are sort of special classes of subclasses of normal linear transformations. Okay. So, we will go ahead with proving the finite dimensional spectral theorem, finite dimensional spectral theorem. Okay. So, in simple words it says that if I have a normal linear transformation on Cn, then I can diagonalize it. So, diagonalization means that there exists an orthonormal basis with respect to which this particular linear transformation looks like a diagonal matrix. So, diagonal matrix is very easy to deal with, and so this is one of the important theorems in finite dimensional cases. So, let us write down that if T from Cn to Cn is a normal linear transformation. So, is normal, which means that T star T is equal to T T star, T and T star commute, right, that is what you mean by a normal linear transformation. Then there exists an orthonormal basis for Cn. So, remember we started with a standard orthonormal basis, right, E1 E2 En for Cn, and what we are saying is once we have a normal linear transformation, then with respect to that normal transformation there is a particular orthonormal basis for Cn with respect to which T acts diagonally. So, the matrix form of T will look like a diagonal matrix. That is same as saying there exists an orthonormal basis for Cn, let us say V1, say V1, V2 etc. Vn, right, you need n of them because they are dimension, you have dimension n, and T acting on V1, V2, Vn is simply by scalars, right, and T of Vj equal to lambda j Vj, okay, where lambda j are some complex numbers, right. So, the lambda j are called the eigenvalues, right. So, lambda j are called the eigenvalues of T. Okay. Some of them may repeat. So, I am not saying the lambda j's are distinct. You can write the spectral theorem in several form, which we will of course do. You can collect the eigenvalues which are same and write down the corresponding eigenspace, and what we are seeing is this, the space, the whole space Cn decomposes accordingly. Okay. So, the matrix form would be, so let me also write down that matrix form. Matrix form is that. So, T has a matrix form, let us say A, if A is normal, if an n by n matrix is normal, what does that mean? A star equal A star A equal to A star, and in this case A star is simply A transpose conjugate, right. That is the matrix if you get, if you use the inner product definition and write down the matrix for T star. Okay. Then there exists a unitary matrix, then there exists a unitary matrix U such that when you conjugate with U, so that is U A U star equal to D, where D is a diagonal matrix. So, it is lambda 1, lambda 2 etc., lambda n, and everything else is 0, right, and lambda j are of course the eigenvalues for the matrix A, which is same as the set of eigenvalues for the linear transformation you have. Okay. So, the U, what does U do? U is a unitary matrix, and so it is only changing the orthonormal basis. So, that is equivalent to the earlier statement we have written down. Okay. So, these are things anyway you are supposed to know. So, we will not spend time on it. Okay. Alright. So, our aim is to prove this. So, let us assume A is normal, A is a normal matrix. So, either matrix or the linear transformation, as I mentioned in the beginning, it is going to be the same. Okay. So, A and A commute. Okay. Now, first of all, we will get one. So, what are these lambda 1, lambda 2, lambda n in the diagonalization procedure? They are going to be the eigenvalues of the matrix A. So, we need to say that A has an eigenvalue, right. First of all, A has eigenvalues. Okay. How does one prove that? Well, so you look at the determinant of A minus lambda I. So, consider that something which you have already seen using fundamental theorem of algebra and so on, right. So, consider the polynomial lambda going to determinant of A minus lambda I. So, I is the n by n identity matrix, right. So, if you look at this is a polynomial, and so by fundamental theorem of algebra, there exists lambda 1, let us say, or let us put lambda naught, okay, such that in the complex plane, such that determinant of A minus lambda naught I, that is the polynomial evaluated at lambda, is 0, right. So, any polynomial has a 0, that is what the fundamental theorem of algebra will tell you. So, hence that is A minus lambda naught I is non invertible, and since you are in the finite dimensional case, this implies that there exists some vector v in Cn such that A minus lambda naught I acting on V is 0, right. It has to kill some vector, the kernel has to exist for it to be non invertible, which is same as saying A V equal to lambda naught V, right. So, this is an eigenvalue. So, this is one of the advantages of the finite dimensional case, because proving that eigenvalues exist is easy. When you go to infinite dimensional cases, there are operators for which there is no eigenvalue, okay, that can happen. Okay. So, let us continue. Now, things are easy, because once you have one eigenvalue, you can go to the orthogonal complement of that particular eigenspace and then continue this procedure. Okay. I prefer to do this in this way, because this is precisely what you will do in the case of infinite dimensional Hilbert space and a compact normal operator. Once you get an eigenvalue, you can go to the orthogonal complement, but that is possible only with the normal operators or normal matrices. Okay. So, let us start. So, let lambda 1 be an eigenvalue for A with eigenvector V1. Okay. So, we want to see what happens. So, A acting on V1 is simply lambda 1 V1, right. So, define V1 perp. So, what is V1 perp? Remember, we have a inner product and so on. So, you look at all those vectors which are orthogonal to V1, right. So, this is going to be all those vectors in Cn which are orthogonal to V1 equal to 0. Okay. Now, this is a subspace. So, this is a subspace of Cn dimension equal to n minus 1, right, because you are looking at V1 and its orthogonal complement. Now, the claim is claim is the space V1 perp is invariant under A and A star. Okay. So, remember A star is the adjoint of A. We are saying that this space is invariant under A and A star. Okay. And then you can restrict A to the the subspace V1 perp and continue. Okay. So, to prove the claim, so how do you prove the claim? Okay. So, to prove the claim, well, what do I want to show? I want to show that V1 perp is invariant under A and A star. First we will prove that. Okay, so first we show that A star, that is the adjoint of A, acting on V1. V1 remember is a eigenvector for A. This is lambda 1 bar V1. So, if A acts like lambda 1 on V1, A star has to act like lambda 1 bar. That is what we will show first. So, that the space spanned by V1 is invariant under both A and A star, and the normality property should tell us that it is true for the complement as well. Okay. So, note that. So, let us see why this is happening. Note that I want to show that A star acting on V1 is lambda 1 bar acting on V1. Okay. So, look at A star minus lambda 1 bar identity into A minus lambda 1 identity, okay, minus A minus lambda 1 identity and A star minus lambda 1 bar identity. Okay. So, that is just, so if you look at this as a matrix B, then it is B star B minus B B star, right. So, it's one term and it's adjoint, right. So, if it is normal, you see that this is 0, right, this is 0 because A and A star commute. So, if I multiply and then expand, you will see that this is 0 because A is normal, because A is normal. Okay. Hence, well, what do? I apply this operator on the left hand side, that matrix on the left hand side on V1 and then take inner product with V1. So, I will get 0 because I am applying the 0 operator or the 0 matrix, right. So, the first one applied to V1 inner product with V1 will be same as the second one applied to V1 inner product with E1. Okay. So, A star minus lambda 1 bar I into A minus lambda 1 I V1 inner product with V1. Okay. So, there is a minus something, that is 0 and that goes to the right hand side, right. So, this is equal to A minus lambda 1 I A star minus lambda 1 bar I V1 inner product with V1, right. That is, well, what will happen to this. So, you look at this term is the adjoint of whatever is here, right. A minus lambda 1 I, if I take the adjoint, I will get A star minus lambda 1 bar, right. So, I can take this to this side by the definition of the inner product. I will get the left hand side to be equal to, so then it would be A minus lambda 1 I acting on V1 inner product with the same thing. So, that is just the norm square, right. So, that is A minus lambda 1 I V norm square is equal to, similarly if you look at this term, this is the star, the adjoint of whatever is here. So, I take this to this side, I will get the star of A minus lambda I, which is A star minus lambda bar I, and so I will get the norm square of A star minus lambda 1 bar I acting on V1, the same vector, right. There is a square here. Okay. Well, what do we know about this guy? A minus lambda 1 I, because V is a oh, I should say V 1, right, sorry. So, V 1 yeah, V 1 is an eigenvector for A with eigenvalue lambda 1. So, this is equal to 0, okay. Hence, this is equal to 0, but this implies that A star V 1 equal to lambda 1 bar V 1, right, and that is what we wanted to show, right. So, we proved that if A is normal and V 1 is an eigenvector with eigenvalue lambda 1, then V 1 is an eigenvector for A star with eigenvalue lambda 1 bar. Okay. So, now we can continue with the proof of the spectral theorem. Okay. So, okay. So, we showed that the so we started with A V 1 equal to lambda 1 V 1, and we showed that A star V 1 equal to lambda 1 bar V 1, right. And we are looking at the space, the orthogonal complement of V 1, that is all vectors such that they are orthogonal to the eigenvector V 1, right. Our claim was that V 1 perp is invariant under both A and A star. Okay. So, how do I show that something is invariant under an operator? I take a vector from that space, apply my operator and see what happens. Okay. So, take Z in V 1 perp. Okay. I want to show, so need to show that A z and A star z are in V 1 perp, right. That is the are in V 1 perp, right. That is what you mean by it is invariant under both A and A star. But that is now easy, because how do I show that something is in the orthogonal complement of some vector? I just take the inner product with that and see what happens. Well, this is Z inner product with A star V 1, but A star V 1 is lambda 1 bar V 1. So, the lambda 1 bar comes out as lambda 1 Z V 1, but Z belongs to V 1 perp. So, the inner product is 0, right. Similarly, A star Z inner product with V 1 is equal to Z inner product with A V 1. A V 1 is lambda 1 V 1, it comes out as lambda 1 bar because it is coming from the right hand side, Z V 1, and this is 0, right. So, A z is inner product with V 1 is 0, and A star Z inner product with V 1 is also 0, right. So, this implies that both A z and A star Z are in V 1. Okay. So, that takes care of the first claim that V 1 perp is invariant under both A and A star, right. So, we have got this decomposition. So, what we have is we have the whole space C n to be decomposed into the span of V 1, right. This is simply the span of V 1, because anything in span of V 1 is simply multiplication by a scalar, right. Direct sum, the direct sum is an orthogonal direct sum V 1 perp, right. Okay. And this portion is invariant under A and A star, and this portion is also invariant under A and A star, right. So, if I choose V 1 as my first basis element, the matrix of A, so choose a basis with V 1 as the first element. So, choose an orthonormal basis, right, V 1 as the first element or first element. Well, V 1, one should assume that norm V 1 is 1, right, if you want an orthonormal basis. So, you can assume that norm V 1 equal to 1. The remaining elements will have to come from V 1 perp, right. The if you choose a basis orthonormal basis, so let us call that script B, then the matrix for A with respect to the new basis B will look like so I am applying A to V1, I will get lambda 1 V1, lambda 1 will be the first entry in the matrix, and it does not have any components in the other portions, right. So, it is 0 0 0 and so on. Okay. Now, if I take any other element, any basis element from V1 perp, that is the orthogonal complement of V1, applying A to it gives me something in V1 perp itself. So, it has no component in the V1 direction, right. So, it is like this, and here I have an n minus 1 cross n minus 1 matrix, right. This is how A will look like, right. And what is this? This matrix is simply A restricted to the space V1 perp, right, because both A and A star are invariant under V1 perp is invariant under both A and A star, right. So, this is simply the restriction of A to that subspace, and so check that, maybe I should write here, so save some space. So, check that A restricted to V1 perp is normal. Okay. A restricted to V1 perp makes sense because V1 perp is invariant under A and A star also leaves V1 perp invariant. So, it is actually a restriction, right, there is no projection involved there, and it is normal there because this is how the matrix looks like. So, if you multiply the matrices, you will see that that portion has to be, that n minus 1 cross n minus 1 matrix has to be normal, and then you can continue, right. So, once you have a normal matrix on a, so now you have an n minus 1 dimensional space and you apply whatever we did earlier, here there is an eigenvalue and so on, right, you continue. So, continue to get a diagonal form for A, right. So, what did we do? We get two things. One is the whole space C n gets decomposed into eigenspaces of A. Okay. So, this is equal to, so let me give some notation for all this, because that is something we will use in the infinite dimensional settings also. So, let sigma A be the set of eigenvalues for A, and we can so some of the eigenvalues may repeat. Okay. So, when I write sigma A, the repetition is not there, it is a collection of distinct eigenvalues of A. Okay. We can write the space C n as direct sum, it is an orthogonal direct sum of kernel of A minus lambda, right, lambda belongs to sigma of A, spectrum of A, right, and restricted to each of this space. So, what is kernel? Kernel is all those, so kernel of A minus lambda, meaning this is all those vectors such that A v equal to lambda v, right, the corresponding eigenspace, right. So, eigenspace with eigenvalue lambda, right. So, your whole space decomposed into these eigenspaces, the eigenspaces are orthogonal to each other, and with respect to this decomposition. So, if you look at each of these spaces, on each space kernel of A minus lambda, A acts like lambda, right. So, if I take a vector from kernel of A minus lambda, let us say Z. A Z is simply lambda Z, right, because it is in the kernel of A minus lambda. So, it is simply multiplication by lambda on that eigenspace, and that is precisely the diagonalization of the matrix A. Okay. So, I will stop with some easy exercises from the diagonalization thing. Okay. So, exercises. Prove that if A is normal, so prove that if A is normal, is self adjoint if and only if spectrum of A is contained in the reals, right. The eigenvalues are contained in the reals. That is one. Prove that if A is normal, then A is unitary if and only if spectrum of A is contained in the circle, unit circle, right. All these are easy corollaries to the finite dimensional spectral theorem. So, we will stop here and we will continue in the next lecture with the infinite dimensional case. Okay.